The sunrise is one of the most beautiful parts of our day. One of the cool things about Alpha Centauri is you get to watch the sunrise 3 times a day. So today we are back to the Outward Bound series to look at colonizing Alpha Centauri. Our interest today deals with binary stars or multiple star systems and how these will influence our ability to colonize them. As we will see today, Alpha Centauri has some special complications to it which might actually make Alpha Centauri not the first one we'd want to colonize. We'll get to those problems in a bit. This episode is longer than usual, so you might like to get yourself a drink and a snack before we begin. Let us make things more interesting today, and as a thought experiment, make it imperative that we colonize Alpha Centauri within the near future. Let us say that we detect a rogue stellar mass black hole about 10 times as massive as our Sun heading towards our solar system that will not just graze past us, which would be bad enough, perturbing orbits, possibly ejecting planets, and ensuring constant hails of comets and asteroids, but is going slow enough it will actually settle into a binary orbit with our own Sun, and drag it out of this area of the galaxy in the process. It may even start eating it. The only silver lining is that it is going slow enough that we can contemplate an evacuation over the next couple centuries. Despite the problems with Alpha Centauri, we decide to colonize it. The main reasons for this are that there is not just 1 but 3 stars in that system. Humanity has learned the hard way not to put all of its eggs in a single basket, and in the Alpha Centauri system we have 3 star baskets for our precious humanity. Another reason is that the system is the closest to Earth, being an average of 4.37 light years away. When the date arrives to pack up all of humanity and move them in bulk, the most economical way is going to be a combination of stellasers and the interstellar laser highway system we've previously discussed. Normally you'd have to build one for each system, but another advantage of going to Alpha Centauri is you could service all 3 stars with just one, and shorter is better for such a highway. If multiple colonies are established around those stars, even the furthest ones away will be able to receive radio messages transmitted from each other within 2 months. Now 2 months sounds like a long time, but empires did very well here on Earth with year-long communication delays back when the only way to get around the world was by sailing ships. We know it is doable, so we can keep the colonies relatively cohesive for at least a time. We also know we can evacuate Earth, and I recommend watching our recent episode on that. We decide to evacuate and send out colony ships, an initial vanguard to set things up, and a vastly larger armada to follow in several waves later. As is the case throughout the series, it's not the journey that interests us, or the spaceships that get us there. We've looked at those before in the Spaceship Propulsion Compendium and the Interstellar Travel Challenges episode. We also looked at what life on an interstellar arc ship would be like in the Life in a Space Colony series, Episode 2, Life on a Colony Ship. However, as I said earlier, our preferred mode of transport to get there is a combination of stellasers and the Interstellar Laser Highway. Now Alpha Centauri is a star system, not a star. Alpha Centauri consists of 2 large stars, one a bit brighter and one a bit dimmer than our own, which orbit each other every 80 years and get as close to each other as Saturn and the Sun do, and as far apart as Pluto and the Sun. The larger is Alpha Centauri A, the smaller Alpha Centauri B. However, there is also a third star, Alpha Centauri C, more commonly known as Proxima Centauri, which is actually the closest star to Earth. Each planet orbits its closest star in that system, not all the stars at once. There is a debate whether Proxima Centauri is a visitor to the Alpha Centauri system or a permanent member. If it is a permanent member, it is right on the extreme edge of being part of the Alpha Centauri system. If we use the analogy of the A and B stars as being a city center, Proxima is at the very outer edges of the rural outer suburbs, almost completely independent from A and B, at 1/5 of a light year away from them, and only very weakly gravitationally bound to the system. At 13,000 AU distance from the other stars, Proxima orbits the A and B system only about twice every million years. Now, while Proxima Centauri is the closest star to us, we can't see it with the naked eye. Alpha Centauri A is just 10% more massive than our own Sun, but 50% brighter, and B is 10% less massive than our Sun and half as bright, a third the brightness of its partner. Proxima, on the other hand, is only about an eighth of the Sun's mass, and 600 times dimmer than our Sun. After an epic 4.24 light-years journey, our colony ships arrive in the Alpha Centauri system at its closest star, Proxima Centauri. The star is a red dwarf. Its habitable zone, or Goldilocks zone, where water can exist in liquid form, is much closer to the star than our Sun's. We already knew it has a planet in its habitable zone, called Proxima b, something we confirmed by sending probes out ahead of the colony ships. We suspected that planet was rocky, and one would like to think that it would be likely we could find life there, or at least make that planet habitable for us. To our relief, the probe shows that the earlier remote observations from Earth were correct, and Proxima b is indeed a rocky planet with 1.3 times Earth gravity. Also in its favor, Proxima Centauri will survive much longer than Alpha Centauri A or B or even our Sun. Its expected lifespan in the main sequence is 4 trillion years, about 300 times the current age of the universe. Being so weakly gravitationally bound to A and B, it is also likely that it will leave that system sometime in the future, and well before A or B go nova at the end of their lives. For humans at Proxima, from a system longevity standpoint, we are trading up in a big way. So far, so good. This is a place we want to settle. However, we have to come to terms with several big issues. Firstly, Proxima b is only 0.05 AU, 7.5 million kilometers, from its star. To put that in perspective, it is 8 times closer to Proxima Centauri than Mercury is to our Sun. While that is the perfect distance to get temperatures that allow liquid water to exist from the much reduced light from Proxima Centauri, the problem is that Proxima Centauri is a variable star. That means convection in the star's body creates magnetic fields that result in random and frequent flaring, generating not only very bright outbursts, but also a total X-ray emission similar to that produced by our Sun, even though Proxima Centauri is much smaller and dimmer. On Proxima b, this will cause massive random increases in deadly X-ray radiation as well as UV, visible, and infrared light. To give you an idea of the scope of the problem, in August 2015, the largest recorded flares of the star were recorded, with the star becoming 8.3 times brighter than normal. Imagine standing outside on Earth on a warm sunny summer's day when the sun suddenly gets 8 times brighter and hotter, and you start to understand the problem. That amount of radiation is more than enough to fry and sterilize a fledgling colony that close into the star. Another problem is that Proxima b was expected to be tightly locked to Proxima Centauri, meaning the same face always points at the star. Yeah, all probes confirm this too. There is no day-night cycle. We have long suspected that red dwarf planets in the habitable zone will lack atmospheres. The solar wind is expected to be more than 1,000 times that of our own Sun, which should be more than enough to blast the atmosphere off any rocky planet that strays too close. In Proxima b's case, this is made worse by the star's regular flaring too, which causes even more solar wind in short bursts. Our probes confirm our suspicions. Proxima b has little to no atmosphere. The spectrum of the red dwarf also means that it puts out more infrared radiation for the same amount of visible light as on Earth, even when it is not flaring. This means that if we want the same amount of visible light as on Earth, we are going to be receiving much more heat. Alternatively, if we want the temperature to be cooler, we have to put up with less visible light. We have regularly taken on the persona of a character we call our Traveler at various times in our Outward Bound series. This episode is a thought experiment and therefore not strictly canon, but we will reintroduce our Traveler here too, to get a human perspective on all of this. This time, he is a senior engineering crew member on the colonizing ships. We huddle around and ask, how can we colonize the system without getting fried, irradiated, or living in perpetual light or darkness or even twilight? Now, we've discussed space habitats quite a lot on the channel, and you will know they are a favorite of mine for colonization, because we can control every aspect of the environment and can fully customize it to our needs. As we discussed in the Life in a Space Colony series, it's an interesting backwards aspect of colonization that you build your basic space stations before you colonize your planets, and of interstellar colonization that you'd also start with space habitats before colonizing planets. This allows us to circumvent the lighting problems of Proxima Centauri, as we can internally generate lighting by fission, fusion, solar power, or the use of mirrors to reflect in Proxima starlight, but coded to reflect away harmful or unnecessary waves, with the remaining useful wavelengths entering a window in the habitat, as well as being able to rotate off-axis so we can simulate a night phase or avoid reflecting too much light in during a flare. Each of these designs is very different in its requirements and internal environment, which compounds the issue of figuring out which design is optimal to build. Tempos flare and tensions run high, so in the end, no one design wins and, instead, a variety of designs are proposed and adopted for a swarm of habitats to be constructed to surround the star at various distances. That's all very well and good, but we now need the materials to actually build these habitats. There are other small, cold planets, asteroids, and comets around, but they are not as easy to get to compared to Proxima b. Proxima b is a great candidate for mining as it is higher than Earth gravity and could stand to lose some mass as a result to make it more Earth-like. The extra gravity is not particularly difficult for fit people to live with either, even with the apparent increase in weight. We set about creating a mining operation supported by a planet-based colony for those who prefer living on a planet instead of living on a space station. We initially established a small colony and nearby mining facility facing the star with direct overhead sunlight. This maximized the solar energy collected using conventional solar panels, but exposes the area to random, deadly radiation flares. As a result, the colony and mining operations are installed into lava tubes under the surface that provide protection from the radiation and micrometeorite bombardment. As the lava tubes are mined, the empty space created is converted into living space. Our probes show that Proxima b turns out to be an iron-rich planet similar to Mars in geological makeup. This is good for making structures, but it is lacking sufficient quantities of other elements vital to life. So we send out small spacecraft to locate smaller, icy bodies orbiting Proxima Centauri further out that have trapped carbon, nitrogen, and water ice. We wrap these bodies in insulation to prevent them from boiling away as they approach the star and sling them towards Proxima b. When they arrive, we process them into water, atmosphere, and other materials for our future colonies. Mined minerals are mass-driven from the planet's surface into orbit. Even with the increased gravity, the lack of an atmosphere means mass drivers are a good way to get mined materials off the planet, at least in the beginning. After we have mined enough material, we will use that material to build an array of space mirrors, and we will build a second larger colony on the permanently dark side of Proxima b, away from the hellish radiation bursts. We dome this over and supply power to it using the array of orbital mirrors that reflect the light from the star to the solar panels on the ground. We even reflect light from a special group of mirrors in the array that have the selective frequency reflection technology we designed for the habitats directly into the dome colony. The mirrors mean that little of the damaging radiation reaches the colony. It also means that we establish light and dark cycles on demand. So we create a day and night and control the light levels, even during a flare, by quickly rotating the mirrors so that less light falls on the domed colony. Even on the dark side of Proxima b, our design ensures that the colony is not in perpetual darkness. Point defense systems take care of any space debris that would hit the domes. We build orbital rings and skyhooks, and this helps to get materials off the planet a lot more easily. We also build nuclear power plants to help supply the increasing population and energy needs of the colonies. Now, Earth's sun is 600 times brighter in all spectrums, but it is 200,000 times as bright in the range we can see than the light hitting Proxima b. This means that on the day side of Proxima, it is still not very bright to our eyes, though it would still be bright. The sun is 400,000 times brighter than a full moon on Earth, for instance, and certainly doesn't seem that way as our eyes are logarithmic in their sensitivity. As a result, since we are filtering the frequencies of light hitting our mirrors, we actually reflect more visible light from Proxima onto our night side colony domes on Proxima b than normally hits the day side of the planet. The dark side now seems brighter than the day side, at least those parts the mirror are lighting. The second colony and its infrastructure allows us to really ramp up mining, and we are soon producing the smaller O'Neill space habitats. In short order, we have enough habitats to offload our colonists into, those who came with us, and the billions soon to begin arriving from our home solar system. It will be a constant squeeze and strain on the life support systems and food reserves, as each new arrival is almost immediately tasked to mining or habitat construction. But as time goes on, there will be ample room for the population as more habitats are produced and humanity spreads out into the mix of habitats around the star. That is the cue for the colony ships to gear up for the next leg of our journey. Proxima Centauri is only the first of the stops on our journey. We have 2 more destinations ahead. It's time to leave, but before we go, we take the opportunity to visit the colony on the dark side of Proxima b. The dome inside looks very much like Earth, with plants, animals, and arcologies living under a domed roof that receives what appears to be perfectly reproduced sunlight supplied by an orbital mirror array. And we are invited to step out from the dome in a spacesuit by an astronomer friend and walk on the barren rocky surface of the dark landscape. We gaze up and, even though we are in an alien system more than 4 light years from our homeworld, we are surprised that the stars look the same as those from Earth, and we see all of the familiar constellations and stars we would see from home, with one exception, a bright new star near Cassiopeia, which is the sun from our home system. We can't see it with our eyes, but we know even as we build here, vast lasers are being built in orbit of the sun to push new and giant ships our way at high speeds, and we will soon need to build our own around Proxima Centauri to slow them down. 40 trillion kilometers from us, the most massive construction project in history is working to build a laser highway and the ships which will venture onto it. We are told by our friend to gaze at the horizon. As we do, we see an even brighter star begin to rise. It is easily the brightest star in the sky and noticeably brighter than Venus was at its brightest from Earth, which was only barely visible during daytime. The star we see is our next destination, the binary pair of Alpha Centauri A, with a magnitude of -6.6 and B with a magnitude of -5.3. They are so close together at this distance that we see them as one blobby star. Our friend says they are so bright she has seen them with the naked eye from the surface of the day side of Proxima b. They are brighter here than Venus is on Earth, and the days here are much dimmer in the visible range of light. This raises an interesting point in terms of my introductory remark about getting to see the sunrise 3 times a day. Proxima b has no natural days or nights, and the stars rise because of the 11-day orbit that Proxima b has around Proxima Centauri, meaning we would see these stars rising and setting in an 11-day cycle. To be honest though, this is a bright star in the night sky, not a sun, so this is not a sunrise the way we were expecting it. Technically, there are no sunrises here, and any that exist are courtesy of our orbital mirror array. Our friend points out that Proxima is actually at its farthest point in its orbit from the binary pair, A and B. Proxima will get 4 times closer, and as it gets closer, the A and B binary will get brighter in the sky, and we will probably be able to tell them apart too, even with the naked eye, in about 250,000 years. That experience spurs our interest to move onwards in our journey, and we leave Proxima excited to visit humanity's first binary pair. The somewhat depleted colony ships head off for a 0.2 light-year journey to the Alpha Centauri A and B binary pair with the remainder of humanity's vanguard. The 0.2 light-year journey is nothing compared to the journey that ships made to get to Proxima Centauri, and this will be a much shorter trip. So what awaits humanity in its first visit to a binary pair? You've probably heard that most stars are binary or multiple star systems, but that's actually wrong. The bigger a star is, the more likely it is to have a companion, which makes sense when you think about it. More mass to pull things into orbit, and more mass in that area to have formed another star. It was a lot easier to spot the bigger stars and their companions in early astronomy, so it skewed our figures. According to current data, about 2/3 of star systems are singular red dwarf systems, Due to their low luminosity, we couldn't detect many red dwarfs until fairly recently, and even Proxima was only discovered in 1915, in spite of being nearer to us than any other star. We normally classify binaries into two types, close and distant, but they can be anywhere from barely bound together, like with Proxima, where residents wouldn't even know they lived in a binary till they developed advanced astronomy, to so close together they were literally touching, and sharing a column of gas between them, akin to the Roche worlds we discussed in the Double Planets episode way back. For our purposes today, we will define three kinds that are reasonably habitable: close, medium, and far. For colonization, we really aren't interested in ones where two binaries that are practically touching, or one that is a short-lived supergiant. So we will say close is where the stars are close enough together that a habitable planet could orbit both in something vaguely approximating a normal orbit. Medium is where the planet would orbit one, but the other is so close it seriously impacts the weather and biology. And far is where it's just a very bright star, if that, no more impacting life on that planet than Mars or Saturn impacts us. For this last case, Proxima is an example. Stable planetary orbits are a major issue for close binaries, and still there for the medium variety, but let's start with the first type, a planet orbiting both stars. This is known as a circumbinary planet, and we found a fair number of these around stars as old as our own, so we can say they can be stable long enough for life to evolve. Orbital stability is only guaranteed for a planet if its distance from those stars is significantly higher than their distance from each other, which means circumbinary planets are outside of the habitable zone for all binary systems other than close binaries. You can't have a habitable planet that orbits two stars who don't have overlapping habitable zones. A planet orbiting both those stars will see the stars orbiting each other much more often than the planet completes an orbit around both, which might make for some weird calendars, and those sun orbits replacing your month or seasons, and indeed they will have big tidal and climate effects. That's not the only weird calendar issue either. Earth technically does not orbit the Sun, but rather the common barycenter of the solar system. Since the Sun is 99.8% of the mass of the solar system, and half the remainder is in Jupiter, that barycenter is usually between the two, but much closer to the Sun, either inside it at times or just above the surface. The Earth-lunar barycenter is in our planet's mantle, but regardless, the Earth spins every 24 hours, and the Sun is pretty much in the same place. In fact, the Earth spins 360 degrees every 23 hours and 56 minutes, a sidereal day, and we need to spin a bit more to see the Sun rise again, an extra 4 minutes. Around a close binary, that is not so. Your planet will still have a sidereal day of fixed length, but neither of those stars is going to rise at the same time throughout the year, or even reset once a year. Sometimes they'll both rise at the same time, sometimes hours apart. Meaning even if your planet wasn't tilted like Earth is, your day length is going to vary over the course of a year, and your shortest days, your winter solstice, where both suns rise and set about the same time, will also have your brightest noon, with both directly overhead at the same time. And this will happen multiple times throughout the year, as they orbit each other much more quickly than the planet does, so again, a good alternative to months or classic seasons. Of course, your planet can have axial tilt too, and likely will, and it can also have a moon. That moon will be a bit weird too. Our moon orbits us once a month and appears full when it is on the opposite side of Earth as the Sun is, and a new moon occurs when it is between us and the Sun, or nominally between. When it actually intercepts the Sun-Earth orbital plane, you get eclipses. Every solar eclipse is also a new moon, and every lunar eclipse a full moon. Needless to say, just like shadows cast in a room with two lights, having two suns changes all of this. Again though, the stars need to be closer to each other than the planet for a circumbinary planet, so full moons won't be a single moment of maximum illumination, with a night or two where the moon appears basically as a circular disk, but rather will last several nights. Alternatively, a new moon with no visible disk at all would only ever occur if those two stars were eclipsing each other. And even when they all lined up the same east and west, they are likely to be a bit up and down from each other, not actually eclipsing, in which case your moon might show a decent crescent on top or bottom. Depending on the specifics of a system, such a new moon might happen fairly regularly, or so rarely it's a major historical event, and solar eclipses where both stars and moon are all lined up ought to be super rare or impossible. For a circumbinary planet though, there are still decently long night times. Just as we have places where the sun doesn't set for months at a time, up near the poles, they would too, only lower and longer. While those two stars will both be very bright and visible, even if one was only a red dwarf, they still will both appear white to the eye. But there will be noticeable variation in coloring of objects on the planet based on which suns are up, much as clothing colors are more or less vivid in daylight, incandescent bulb, fluorescent, or LED. You might also expect some changes to plants too, as they not only have to adjust to light changes over the day and year, but intermittent changes of day length and brightness over periods of maybe a month or two. However, Alpha Centauri is the other type of binary system I mentioned, the medium case, and that is very different. Here, the stars are far enough apart no planet could orbit both and be habitable or stable, but also far enough apart that a planet could be stable and habitable around just one. There is a gap, by the way, where a pair of stars are too far apart for a habitable circumbinary planet, but too close together for a stable orbiting planet around just one of them. Non-circumbinary planets orbit just one of those stars, also called S-type orbits, and they need to be at least 5 times closer to their primary than the other sun or be disrupted, and that value is very dependent on the relative mass of those stars to each other and their orbital eccentricity. Alpha Centauri A and B are 11 AU apart at their closest, 11 times farther apart than Earth and the Sun, and have a mean distance of double that, so habitable planets are viable here. A is bigger, so a hypothetical planet around it would need to be a bit farther away from its sun than Earth is, as it is half again as bright and would provide illumination comparable to Earth's at 22% farther away, and would have an orbital period of 470 days instead of 365 at that distance and that sun's mass. Needless to say, it could be closer or farther, or very different in mass, and we hardly have to abandon it if it is. We already discussed colonizing places like Venus, Mars, or various gas giant moons, and we have just successfully colonized a hostile variable stars planet, Proxima b, that makes those others look like child's play. So, we get back to our story at this point. We send out probes again to both stars, A and B, and confirm the existence of a rocky planet exactly where we want it, in that habitable zone in orbit around A. We name it Aurora, and we find a similar planet around B that we name Boreas. Both are around the same mass as Earth. Needless to say, we are overjoyed by this lucky coincidence. We are not too likely to find life on any planets or moons in the Alpha Centauri system, at least not if we don't find it in our own solar system first, which would imply it pops up and sticks around virtually anywhere. But making life there is actually quite viable. We confirm that there is no life on either Aurora or Boreas, but both planets have thick atmospheres, similar to primordial Earth, that makes terraforming them relatively easy. Alpha Centauri b is dimmer than A, and its closest approach to Aurora is 10 AU, about the same distance as Earth to Saturn, while its farthest is farther than Pluto, and it changes over an 80-year cycle, or more like 60 Auroran years. We land on Aurora and gaze up at the night sky. We see B at its closest is still less than a percent as bright as A, but even at its furthest, it is far brighter than a full moon. It will noticeably move around the sky over the years like planets do, but again its whole progress is over 80 years, not a month like our moon or a year for the sun. Proxima was 13,000 times farther from us than our sun is from Earth, and only a 600th as luminous. And indeed it's not even that bright to our eyes, as it gives off far more of its light proportionally in the infrared spectrum we can't see. That 600th is its bolometric luminosity, its total brightness in all spectrums. So 200,000 times dimmer and 13,000 times farther away means it appears to the naked eye some 30 trillion times dimmer. Now, we can definitely see that on a dark night, but it has an apparent magnitude of about 4 or 5, about as dim as we can see. Remember, while it was the closest star to us, we can't see it with the naked eye, and it's only 20 times closer and 400 times brighter to A and B, so we see it as just a regular star and it's invisible during the daytime. We were disappointed at Proxima b because we did not see a triple sunrise, and we are again disappointed, no triple sunrises here either. On the bright side though, there are 2 sunrises. Over the year that we walk on the surface, we notice B circling around the planet relative to where A is. When Aurora is passing approximately in between them, it is a normal day and a very bright night. When B is closest on its 80-year progression, nights are like an overcast day, while at its furthest in 80 years' time, night will appear very overcast to twilight. At the full opposite, when both A and B are aligned with the planet on their far side, the day is just a little brighter than normal, barely noticeable. However, we get a fairly rare event when we get to the nights there where the twilight is replaced by a true night sky. In between that, we experience extended days, with B rising before or setting after for prolonged periods of light in the twilight to overcast range, followed by a genuine but shorter night. As we move around the planet on our various tasks, we experience a lot of places with periods of extended light. Tall mountain peaks and the poles experience protracted periods of having at least one sun up. This is of more than academic interest as photosynthesis can take place, if weekly, and we speculate that this is likely to mess around with all sorts of biological cycles, everything from seasonal growth to the hunting methods and anatomy of eyeballs in species as they evolve on the planet. Life here will evolve along its own path, and species that adapt to the conditions best will thrive and survive. Those that stick to what they did on Earth will decline in the face of those adapters and die out. We are called away to the other planet to be terraformed, Boreas, around Alpha Centauri b. As I said, this is hypothetical, except we don't have to be too hypothetical when it comes to B. We detected a planet around B in 2012. That was later shown to be an error. We did find one around B in 2013. Unfortunately, both the ghost planet and the new one are worse than Mercury in terms of heat, and while we have discussed colonizing hot planets before, or even stars themselves, planets like these would likely only be colonized in the temporary sense of mining them for raw materials to make space habitats instead. Fortunately, Boreas is an Earth clone around B for this, and has an orbital distance of just 0.7 AU, like Venus, to be the same temperature as Earth, and it orbits every 225 days. That 80-year binary orbital period, which appears as 60 local years on Aurora, is going to be 130 local years on Boreas. One would hope that our progress in colonizing star systems will be onward and upward, but history has shown that societies can lose technology and revert to pre-technology civilizations. If that happens here, we will hopefully have terraformed the planet sufficiently for them to exist without technological intervention. Assuming we did regress and then start re-establishing ourselves technologically, natives to either planet are going to have some calendar equivalent of a century that corresponds to that period. Amusingly, its duration would be the same for both, even though we'd say it was 80 years, the Aurorans would say 60, and the Boreans 130. I stress the calendar aspect as civilizations tend to ingrain astronomy and numerology into the mythology, mathematics, and early traditions. Not to mention, we have a lot of authors here or folks who just enjoy world building, so if you're putting together some hypothetical devolved society, alien race, or fantasy planet, those are points to know. Incidentally, if you want to figure these out for yourselves on hypothetical stars, just check the star's brightness relative to our sun. Use the bolometric value, take the square root of that, and that's how many AU away it would orbit. Then you need to calculate its orbital period based on that. Classic Kepler method, but don't forget to change the star's mass. This is harder for a close binary, but still works fine for our medium, non-circumbinary case, where the planet only orbits one star. Or at least it will most of the time anyway. Alpha Centauri A is about 3 times brighter than B, but conditions on Boreas are fairly similar to Aurora. Those protracted twilights or very bright nights are about 3 times brighter, though to the naked eye will seem about the same, and any plants adapted to make use of that light will fare much better and be more likely to thrive. Similarly, while A won't seem nearly as bright in the sky as B when sharing it during the day, It's a lot closer, and a period where A was at noon while B was setting or rising would have A brighter in the sky than B. That might make for an interesting protracted dawn, because A might only provide twilight or overcast lighting, but it will still be blue sky when it's directly overhead, while you get that red outward rainbow from B, so you notice some strange color bands across the sky. You'd have those on Aurora too, but not as pronounced. On the biology of the planets, tides on Earth play an important role in ecosystems. There is some compelling evidence that life could not have evolved on Earth without them. On Earth, we have the tides thanks to the moon, but in Alpha Centauri, to bastardize a quote from Back to the Future, moons? Where we're going, we don't need moons. On an ocean-containing world around Alpha Centauri B or Alpha Centauri A, we would get tides from the presence of the binary star tugging at the water. The stars are much further away than our moon is from our planet, but Alpha Centauri A is 30 million times as massive as our moon, and Alpha Centauri B is 25 million times as massive. The effect of gravity drops off with the square of distance. At the closest, they are about 10 AU away from the planet, compared to a paltry 0.00257 AU for our moon from Earth. This means that for an ocean world orbiting Alpha Centauri A, tides caused by Alpha Centauri B would be 60% higher than here on Earth, and for such a world orbiting around Alpha Centauri B, tides would be double that experienced on Earth. Usually when we want to communicate with other worlds orbiting other stars, communication times are upwards of years, but not in Alpha Centauri, as communicating with our friends on Aurora, they are able to receive radio messages transmitted from here on Boreas in just over an hour, even though they are technically orbiting a different star. We ultimately achieve the same level of colonization in the A and B systems, including the space habitats that we perfected when colonizing Proxima. Humanity is certainly in a different place now, and has come a long way from those early days when we were going to be snuffed out by that black hole. We are now getting excited about using Alpha Centauri as a launch point to colonize the rest of the galaxy, now that we have a colony fleet and lots of experienced colonists sitting around, but that is a different story. If you're curious about some of the propulsion systems that might take us to the stars, try out the Spaceship Propulsion Compendium, and if you want to look more at the journey through space, or those early colony days far from Earth, see the Life in a Space Colony series. However, that is the end of the Outward Bound series, at least chronologically. We might revisit it to add some episodes looking at Mercury or Neptune, or one of the bigger asteroids, but this is as far out as we are going. We've been to the planets, many a moon, and even out to the Oort cloud. We've headed back to colonize the sun, and then out again today to colonize other suns. And from here, it would continue on to our other series looking at interstellar colonization and travel. When I first started the series, I faced a dilemma, and a good one to have no doubt, of choosing between providing a brief overview of the science that is focused on relevant portions, or diving deep into the science but covering much fewer ideas in each video. Neither approach felt right to me, and I didn't know how best to appeal to my varied audience. I was then contacted by Brilliant, which has courses that explore the underlying physics and astronomy for many of the concepts we needed to properly look at here, about a sponsorship opportunity. This made me feel comfortable in covering just what is relevant for a solid understanding of the video, while recommending folks that wanted to explore and master these concepts to check out Brilliant. The first message on the home and transfer orbits was such a perfect fit for the channel, and many of you appreciated the deeper insight that Brilliant offered. We can draw on their quizzes to help us stretch our imagination and discover what else is possible. For instance, if you want to be able to calculate out stuff like how long a planet's year would be in the habitable zone of an alien sun, they've got a great course on Keplerian orbits, and when you're done with it, along with what we discussed today, you'll be able to create any solar system you like and know all of its specifics. Isn't that amazing? Go to brilliant.org/Isaac Arthur and sign up for free. And also, if you are ready to expand your mental toolbox, the first 42 people will get 20% off the annual premium subscription. That's the subscription I've been using to entertain myself with thought-provoking puzzles. We might be done for now with the Outward Bound series, but next week we'll return to the Upward Bound series to continue our look at orbital deployment. and look at some necessities we'll have to have in order to do that. We will also look at Kessler syndrome, the possibility of a runaway destruction of orbital platforms that could leave space littered with dangerous debris, and what we could do about that. In event of a war in space destroying such equipment, you could close a planet off for generations just from the wreckage. The week after that, we will jump back into interstellar space to look at interstellar warfare and find out what the #1 rule governing space warfare will be. And the week after that, we will return to the Civilizations at the End of Time series for Dying Earth, and what civilizations will do when the planet and sun they've always depended upon begin to perish. For alerts when those and other episodes come out, make sure to subscribe to the channel. And if you enjoyed this episode, hit the like button and share it with others. Until next time, thanks for watching, and have a great week.